Hi, welcome back to my channel. Today's video is on OCaml as a programming language. I discussed Haskell briefly in another video, and I wanted to take a look at a language that kind of inspired Haskell in lots of ways, um, and is also another language in the whole family of what is called the ML uh, family of languages that started out with a tool called Standard ML from the Bell Labs that was developed in the late 70s and 80s. So there's also going to be some bonus material on a pretty popular tool that was built on OCaml, and we'll talk about that as some bonus content. So this is just be a brief introduction to getting it set up and my impressions of the language and how it worked, and again some bonus content for those that might be interested in it as a subject. So the setup they have is basically there's a tool called OPAM, which is kind of the OCaml package manager thing, and it's available. You just go to that website, and it's pretty obvious and straightforward. Um, Getting it set up, and not only that, but you can use most package managers to install it. And then, as I develop on Windows, it's one of my most popular videos. Is why I actually do that. Is WinGet. You can just get it with WinGet, and it works great. So that was kind of nice. Haskell, you can still download it pretty easily, and they have PowerShell support for the scripts and stuff like that. So Haskell's Windows support isn't that bad either, but it's just kind of nice to see that they went through the effort of like including it in the WinGet store. So I'd say compare the Haskell tooling, and if you haven't seen my video on Haskell, you can go back and watch that for more context. But compare that Haskell tooling, this OPAM is much more unified and straightforward. Haskell kind of had like tools, Cabal and Slack, the stack that kind of work together. OPAM just seems to do all the things. It takes care of all the libraries for you, and it keeps track of multiple tools and packages and bundling together in what it calls a switch. It's not perfect because you have to remember to switch your environment variables over if you want to go from one to another. On Windows, it can't automatically do that for you. For other environments, you just run the thing and it'll set up the environment for you after run a certain programming. Basically, you just run a certain OPAM command and it'll just set up all your environment variables for you in the shell. So it's just a minor Windows hiccup as well. So that's not a big deal. And so that works really great, and it was very straightforward. You just said, oh, I want to use this version of the compiler, and I want to switch to this other version of the compiler. Easy, well to do. And there's, like I said, there's only two main branches that you would want to deal with anyway, which seems to be now they have a 4x branch and a 5x branch, versus Haskell, which is like they had 9.2 even was in long-term support, 9.6, 9.8, and 9.10, and then a 9.12 branch, all that you could potentially be working in. And again, I really liked how it did this. And not only that, but the thing about it is that not only can you have what they call global switches, which switch back and forth between tools in a global environment, but you can set them up on a per project basis. And since the tools are that big, if you want to actually make sure that for a project that you just tracked a specific version of the compiler and the languages, you can do that on a local system, on a local directory as well. They call them local switches, and it pretty much just does the right thing, and it's actually pretty cool. Again, as I talked about, there's two main branches you have to deal with, 4x and 5x. Some things are not yet compatible with 5x, aren't supported by them, so that's why it's still 4x going on. But there's a pretty good roadmap on how they deal with this. And again, switches compared to Haskell just makes it so much easier to deal with. There's a build tool that OCaml uses called Dune, and it's pretty interesting. It's one of those things where I really much like how they did it, and it's one of those things where you can kind of see that they were thinking about maybe using it past just for building OCaml projects in terms of how it does things. It's kind of a fairly straightforward environment. The thing that's funny to me is that Dune, if you look at it, it's literally it's just S expressions, so it's literally a scheme program that interprets it. If you look at it, it's like, oh, this is just scheme. So that was really interesting. And that kind of makes it pretty easy and expressive and stuff like that. So using it to build stuff, very straightforward. Running it stuff, very easy to do. The editor support, the editor in VS Code is pretty good, as the one in Haskell is. But like Haskell, the debugging is pretty experimental. I'd say that both the Haskell and the OCaml people, for whatever historical reasons, seem to really prefer, be in the Unix and Emacs environment than versus using VS Code. But there's also some realization, obviously, there that there is going to be this kind of VS Code has a certain amount of momentum. That's how you want to really, really support things. And so they have revived some projects around getting the debugger to work better with the VS Code debug adapter protocol. The fascinating thing about VS Code is that between language server and the debugger adapter thing, it's really becoming a way of just for having all the editors, the new ones, have just a standard way of doing an out of process way of handling things for like IntelliSense and all this kind of stuff, so that you can use them between multiple editors. And more languages are realizing that just kind of needs to be a default part of what your language is. If you don't really ship with a language server protocol or debug adapter protocol, then you're not really getting the full advantage of it. And the thing about it is that Visual Studio Code is doing actually a pretty good job of kind of basically creating a reasonable, lightweight default debug experience that could be consistent among multiple languages. And that's really useful. There's no reason to reinvent the wheel in that idea when you basically want to do the basic things the same way in pretty much language. I want to set a breakpoint the same way. I want to be able to watch variables the same way. I don't want to have to use a completely different set of UI abstractions and a completely different layout for every single language. It's a pretty cool idea. So I'm glad to see that's being cut on. And of course, Emacs itself has support for these things now, and so is like NeoVim. So it's catching on just beyond Visual Studio Code as well. So here's what FizzBuzz looks like in a good old Vector Camel. And here you can see if you looked at my if you looked at my Haskell video, you can see we use guard expressions. Here we just use if then or else's. Like Haskell, there is no if then. You have to have an if then else because this is a functional programming language, and it doesn't really make sense to have a function that either returns a value or returns nothing or unit. So it doesn't have that. So this is basically goes through and does what this does. It's a little bit more verbose, but it does the thing. There will also be ways you could do it with case statements and stuff like that, and you can kind of hack pattern matching to do this. But this is kind of the most straightforward way of doing it. And like I said, it's much easier. There's less implicit stuff. If you know how about Haskell, you don't need the let keyword here and all that kind of stuff. And this is what I found is that OCaml is way more forgiving than Haskell in terms of the compiler, providing more helpful errors overall, providing more guidance on why things are broken. And so it really does a lower bar to entry than Haskell does, while still introducing this notion of, oh, I want to use a strongly typed functional programming language that uses type inference, getting a feel for how that works. And something that has a lot of things in common with Haskell in terms of syntax. So again, why learn it? If you really are interested in the strong functional type languages and you've seen Haskell kind of be presented at, I would say OCaml is a really excellent thing to look at because you're going to get 95 or maybe 96% of what you need out of it. And because there's still monads, in OCaml, but you don't have the higher other kinds and all this other generalized abstract data type stuff that Haskell has. And not only that, but you can still fall back to there's support for mutable variables and things like that. So it's just basically it makes more practical compromises there, and that's what makes it fairly interesting. And I would say just basically easier to get into. And the runtime's pretty robust. There's a good community around it. And the thing about it is that this is really going to do if you want to take a look at a language that was designed this way from the ground up versus something that had it kind of like attitude afterwards. Even though I say the hybrid approach is a really big win, especially C#. I see C# is an excellent language that really managed this hybrid object-oriented programming with functional concepts via LINQ and these other types of things really well. And if you take a look at some of the later extensions of C#, things around records and so on and so forth, as well as how they support immutable data structures, they've done a really good job there, I think, in that environment. And Java's catching up as well in that regard. But it is useful to use a language that works from the very beginning and then moves you into other areas when you're ready to. So as a summary, if you want to learn functional programming, Racket is still the best choice, I think, entry level to begin with, just because you're dealing with less syntax. And not only that, but the REPL is really nice to work in. Even though OCaml has a REPL, as well as Haskell does, that read value printlib, it's really easy to start typing in scheme expressions or Racket expressions and get things going. And like I said, Dr. Racket is one out of the box experience that works really well. And that just makes it for a very easy, straightforward, get things going and start doing things with. However, OCaml is a really great choice. I mean, Haskell still would be my last on it if you want to do this way. And consider F# as an interesting alternative, and I will have a video on F# and see how well that is integrated in the .NET tooling and what's going on there and where it differs from OCaml. So for those of you that are maybe not interested in this more advanced topic or don't have like more background in like some of the math and other stuff, this might not be of interest to you. And you can go ahead and just stop the video here. I won't feel badly about it at all. If you really liked it, then please do leave a like and subscribe. But one of the things I did want to talk about was when people talk about these languages, they kind of say it's like, well, who uses them? And there's maybe one or two projects of interest in the language that really show how they're used. But this one was probably the most interesting case to me, and it's a language that's called Rocq. It used to be called Coq, um, and this is all out of a advanced institution of research in France. So that's why they use these French terms. I think they renamed it just because everybody was kind of tired of the people giggling every time they said cock, the cock proof assistant. So they are going, but they're adding some stuff to the language, and so they kind of making a new version that's worthy of having a name change. But it's all written in OCaml, and basically what it is it helps write and check mathematical proofs. And this is a very interesting but advanced topic in computer science, and it's kind of grown a bit as it's gotten some successes in the 2000s, 2010s, and not only that, but as we become more concerned with computer security and things like, having languages that are safe, the kind of notion of proving certain things about code has become more and more interest. So it's kind of in this vein. The interesting thing I would say about this is that Haskell also has a proof proof assistant language that it has been developed using Haskell that relates to it, which is called AGGA, and that stands for hen in Swedish, I believe. And so there's that thing there. I played with AGGA a bit. The tooling is still pretty rough. You really need to be having to use Emacs for it. Not only that, but the libraries and the language uses a lot of Unicode, and I mean a lot. And for the people that really like mathematical stuff that really looks nice, the problem is that when it comes to doing things like on GitHub or reading them, there's some programs out there that you can't literally read because I don't know how to pronounce things like, oh, this is n, but this is n as a natural set, so I don't know what the unit character is. So you have to have all this background in mathematics to know, oh, that's this n is set. That's the set of all naturals and all these types of things. And there's some characters that they use as like, I don't know what that means. And it kind of runs into the problem that a lot of advanced mathematical texts have, which is just can be the sea of symbols. And if you don't know what they are, it can be really impossible to read. And that I found that kind of, okay, a little bit off-putting. There's some interesting things around AGGA in terms of it's how it works and generates into Haskell. And there's a lot of people that really like it compared to Rocq, but they kind of do overlap in quite some interesting ways. And just as an aside, just to make, for the sake of completeness, which is really odd, F# also has a language for verification based on it called F*. And that has been used in some interesting projects as well. So it's interesting that all these three languages that are variations of standard ML also have their variations of a proof assistant. And if you take a look at the language of what you can do with ML, there's kind of a very natural thing to build these kind of systems in. But again, this is a very advanced topic, so you've been fair warned. I'm going to gloss over quite a bit of things. And what I would say that is that you need to go on and install the tools and go through that and really kind of go through the environment to see what's going on and what it allows you to do. It's really good. And the Visual Studio Code integration is excellent. They actually have a separate IDE that I used to use in the past when I was first looking at this stuff. I didn't even bother with it because the Visual Studio Code, once I got it set up, worked excellent. I had no problems with it whatsoever. So what this is all based on is a thing called the Curry-Howard correspondence. And basically what it is that these logicians, mathematicians found out that given a sufficient type system, type checking a program using that type system is a form of mathematical proof. Now, you do have to have a sufficient type system. And about what that means is a little bit more complicated, but it's one of those things where it's not like the simplest of type systems. Basically, you have to have some level of parameterized types, or dependent types to really make this work. But these, and there's multiple type theories that work within this. There's multiple type systems that work within this, and so all these type systems that can be used to do mathematical proofs, they're called modern type. That's called modern type theory, and so that's what these kind of use. And not only that, but it's not any type of program as well. And there's a couple of reasons for that. And the reason, one of the things about it is the one main one is that if you do a proof, what has to happen is the program has to be non-terminating, or otherwise you could prove anything is anything. And there's a really complex way of having to think about that. But basically, it's one of those things where, yeah, if the program doesn't type check and also terminates when you ran it, then you could, yeah, there's just, you can't make a proof that way. But the thing about it is that in languages in general, we know are Turing complete, which means that is going to be an issue. So we can't just take any old like type variant of a language and turns it into a proof, because we know that they're necessarily potentially non-terminating. The way that they deal with this is there's two main ways of going about it. One is to take all the potentially non-terminating parts, stick it in a monad, and then just do the proof checking on the non-nomadic code. And so that's kind of interesting. I think that's what AdGut does. It's really just kind of takes a look at there. There's other people that actually say, you know what, Turing completeness is nice, but you still have plenty of computational power if you don't have a Turing complete language. And what they do is that what they do is they eliminate what's called unrestricted recursion, and they kind of use co-recursion for this. What's interesting there is that what you have to do there is that those languages, in a sense, they have to know that a recursion descends, so that it basically they can analyze some things about the language and the types that are being used and doing it. In general, that actually turns out to be really difficult to do. Outside of certain types, it's really hard to say that this thing will recursively terminate. But there are some languages that do insist on it. And that's the general thing that makes this more difficult is that you either have to do this isolation, but you have to try to make sure that the really useful stuff that you're doing is still being type checked and then proven, versus just being shoved off to the monad and you're not really doing anything but just proving what you already knew, or restricting yourself to the type of types where you can do unrestricted recursion and co-recursion that works. So that's kind of a big issue here, and there's nothing else you can do about it right now. No one else has some additional theories behind this, and so that's kind of where it comes down to. You can also do proof checking outside this through what's called model checking, and basically use a different set of tools that kind of all of them kind of revolve what would you call Boolean satisfiability, to check to see if something works. So that's where Rocq comes in, is that it's this theorem proving language that was built in OCaml. Its most famous usage was in was proving the four color theorem, which is a graph theory thing that says if you have a graph that represents a map, and there's only certain types of graphs that are maps, and you want to color that graph so that each node, its adjacent nodes, or the ones that has edges to, are of a different color. Well, if you have a map, that's something that you could lay out on a surface and say this is a map. Well, you only need four colors to do that on a map. And so every map that you look at, you only need four colors to color them in. That was this big theorem. And it wasn't proved until they did this thing where they reduced the amount of maps from being potentially infinite to a rather large number of exemplar maps. And then what they did is they used Rocq to basically provably color every map and prove that it was correct. And it's the first time that computer-assisted proof was really accepted by the mathematical community as being a good enough. It is a proof that we know now that the four-color theory is correct from mathematically, and it also accepted that basically this kind of thing, where there's potential for brute forcing these types of cases, can be used by the mathematical community at large, because these systems can be trusted to do the right thing. This is an example of the code here, and what I've done here is that I'm going to do some reasoning about natural numbers, and so that's why I've reported this NAT module. This is like basically a bunch of stuff about numbers. And what I'm going to do is I'm going to make a proposition about numbers that are basically, I'm going to define even and odd. And this does match up to what you think of as even and odd in natural numbers. And you can kind of think of one of these things where they're basically, you kind of define them mutually with each other. So this is why there's this with, because they both use each other. But basically it goes on and says this. There's two things. If you have this inductive thing, this is even, 0 is even, right? That's what this says. And then there's this S, this kind of stands for successor. And if you know Pinot numbers, then that's what this kind of comes from. But an n, an arbitrary n, number n, is even if odd. It's one of those things where even as basically the successor of n implies that odd n implies that even 1 plus n is that, stuff like that. So this is a little bit odd, but basically what it is that if you have a larger number, this number that's slightly smaller than that, these two imply each other, and then odd does this. And basically what it does is that the successor of n implies that this means this. So this implies this implies this. And so this is a way of defining even and odd. Not necessarily the most intuitive way of doing it, but there's lots of things that you can do that makes this fairly straightforward. And basically what it does is that, now the thing about it is one of the things is like, well, what if you turned it around? Would it still work? And the thing about it is that Coq is very, very specific about how it does proving. And one of the things that it does is can be very susceptible to lexicographic ordering. And what I mean by lexicographic ordering is that where you put things in. For example, if you turn this around and go n plus 1 versus 1 plus n, you can't do this proof that I'm showing you in the next thing. It just doesn't work. You have to use another set of libraries that know about this and then change things around. So you just have to be aware of that. And this is, again, what makes it very difficult to use by people that don't have a lot of experience with mathematics and programming in general. But once you get to it, you can realize what's going on. Now, that being said, Mono Rocq, they've added a lot of tactics so that in certain domains, writing various types of proofs can be just done through a very simple amount of just grinding down some tactics. And so you don't have to kind of do these very specific steps. But what happens is that when I go in, and I'm going to show you an example of this, is that you can do examples. You can say basically even for is true. This is basically, I'm saying even for, right? Okay, I'm asserting that this is correct. That this proposition holds, so to speak. And here's the proof. What I can do is that I can either apply this even s or odd s tactic until both of them either try to do this or try to do this, bam, bam, bam. And eventually what it'll do is it'll give me this thing where I have to say eventually, oh, I need you to prove that even 0 is true. But then I can just go say, oh, well, you know that even I've asserted that in my definition. Therefore, just apply this even 0 prop to it, and we're done. Okay. And so this is where the taxes come in. It literally crunches things down. So it just basically reduces the thing by 1 every single time until it gets to 0. And then you can basically assert, oh, wait a minute, yes, 0 is even, and then we're done. And QED is the way of saying we're done here. So very interesting type of language. Again, it doesn't really look like Haskell or anything like that, but it's its own syntax that they've used. It's kind of based on earlier stuff called Galena that was used in the 90s. So that's kind of where this comes from. So now if you wanted to do something that said, okay, some interesting lemma about this, which is basically every natural number is either even or odd. And here's the thing. This is the proof of it. You can induce, basically it has this tactic for induction and n, and it does the thing where it does an inductive structure proof where it knows that, okay, well, I need you to prove the 0 case, then I'm going to assume the inductive case, and now I need you to prove that the n plus 1 case works. And so what I've done here is that when I do some end, it asks me for this goal. The interesting thing about Rocq and how it works, and Agga's the same way, the other proof of things that work like this, is it has a set of goals it needs to match. And you actually kind of work with it very interactively to try to get these goals together. And it's a really kind of cool, interesting process to try to solve these types of things. And what the goal does is says, hey, you've already proven a certain amount of things, and if you get it to the point where you have no goals, then congratulations, this proof is correct. And so what I did here is when I did the induction and asked me, said, okay, well, I've induced on this. And so I've given you the proposition that either 0 is even or 0 is odd. And so I basically said, oh, well, okay, first of all, select the left part of that disjunction, and then basically, yes, apply even 0, because that's a proof that even 0. That's by definition. Bam. Okay. Otherwise, it's going to ask me, well, is even n plus 1 or odd n plus 1, given that even n or odd n is true. And so now what I need to do is I need to split this up into two parts. I mean, basically, it's split up into two parts. And this is what this destruct does. It says, okay, split this into the even and odd thing. And now what I need you to do is go off, take the right part, apply the odd s, and then use auto. Auto is just a tactic that kind of says, now just obviously do the obvious things. Very obvious types of things until you can prove stuff like that. But basically, it's like it knows about like 1 equals 1. It knows about very basic types of stuff. And then do this on the right, and then on the left, do this, and then take this. And eventually that will prove it. And you're done. And so this is a mathematical proof. Given my definition of even and odd, every number, not just, every number, not even the ones that just could fit in a computer's memory, but by type checking this, every single natural number is either even or odd. Very cool. Lots of fun to play with. Once you get into more advanced stuff, it gets a little bit more tricky. The thing about this is that what's really interesting is that there's a large set of online textbooks out there called Software Foundations by Benjamin Pierce. And he's at the University of Pennsylvania, and they're available on the website there. Just do a search for Software Foundations, and then Rocq or Software Foundations Pierce, or Software Foundation programming books. You should find them. And he does a whole introduction to programming by using Rocq. And it starts from the very beginning and defines things like, oh, here's how you use numbers, here's how you do lists. And the entire book itself is actually just a set of Rocq programs with a large amount of markup in them. And you can go through this, and then basically what the exercises is you end up completing your own version of the textbook by checking out the textbook code on GitHub, forking it, and then completing those files that are there for the books, and then that's your homework. And it's a great series. It goes into a lot of depth, and it would be a really, really great way to teach programming, except it would be it would take probably about 3 years. And you would not get into the practical applications of computer science that most people would expect you to have. And so it would literally take you an extra 2 to 3 years to get a computer science program. And so as a practicality sake, it doesn't get used very often. It is still taught there. They teach parts of it for the semester. But if you look at the entire set of books that it's built, which is basically up to 7 types of things, literally 3 years worth of study there. And so, a monumental achievement. And not only that, that's all on GitHub. It's all free. And so very interesting. And again, it has this whole tactic library that it used to implement proofs. Agda doesn't use tactics. You have to be more explicit about its goals. But the way it does goals is a little bit smarter in terms of type theory. So there's not necessarily as much hassle. But sometimes Agda proofs could be very, very verbose compared to Rocq type of things. That being said, their verbosity is sometimes what people in the theory think they want. Sometimes they think Rocq theories can a little bit much like, and my hand was waved and all is good. So the interesting thing about it is you can add your own tactics to the core platform, which is in certain domains very, very useful. So, and what a tactic is like if there's kind of things that you do in proving something over and over and over again, well, you can capture that as a pattern and use it throughout your code to make sure you just don't have to repeat it over and over again. It's kind of a way of capturing, oh, I'm doing this proof this way, and so here's how you do it, and here's how you finish it up. Interesting thing about it is you can extract code from certain types of proofs as OCaml code itself, also Haskell code or Scheme code. And so there's an example in which you could take his definition. Benjamin Pierce in the Software Foundation book defines a list and defines 2 propositions. Basically, two propositions. No, not propositions, functions. Excuse me, functions about that insert and sort, and proves that the sort works. And then you can export that code to do an insertion sort. Very interesting, really clever. The practical considerations here. This seems perfect for like improving software quality, and it is. It's kind of actually considered the holy grail of like how we can make software quality better, is literally by adding mathematical rigor to it. The practical cost here of difficulties is just really high. not in terms of the cognitive ability necessary for people to write up and stuff. Computing is very difficult. It just a lot of rigor, a lot of things, a lot of tools, and not only that, but the underlying code that is generated from these proofs may be incredibly unoptimized and slow, and too slow to be practical. And I'll give you an example. There's a project called L4, which they had to go through, and it was a microkernel. And to do this work, and it was used in a previous version, an older proof assistant called Isabel, HOL. And they literally had to go through and do verifications for the source, the tool chain, which is basically the basic compiler that they use to make it, generate binaries. So basically, that all three lined up. The binaries verify that there are certain types of properties that were true about the microkernel, that the toolchain could then take the source and guarantee that the binaries and the source would line up well enough. Just a massive amount of work. But they've been improving on it and doing some more work in there. And it's a really interesting idea that eventually what might happen in operating systems is that they do move back to a microkernel version in which that microkernel does provide some very fundamental, provable operations in terms of process isolation and basically of isolating your resources. So you can't do things like, break out of a hypervisor or, have memory leaks, so on and so forth. So a lot of stuff very promising there. The last thing I'll talk about that was kind of interesting is there's another tool in this vein, but it's actually become more focused about doing mathematical proofs, less in the computer science domain in terms of like translating into programs, but more in the writing proofs in general around mathematics. And instead of just writing these big texts up, writing more of these proofs in a formal programming language that supports it. And the interesting thing about it is that they even want to make this reasonable at an undergraduate level, so that instead of people handing in their homework as just basically a bunch of text or Mathematica, notebook if you're really lucky about here's the steps I did, that they would literally hand in Lean code to show that this is their proof. And then Lean, of course, being the environment that it is, could prove that their code, they understand it, that the proof is actually a proof. And the tooling there is really good. It's especially with VS Code. In fact, their default recommendations for the latest version of Lean is just go to VS Code, install the extension. It will take care of getting the version of the libraries for you and all that kind of stuff, and just interact with it there. And again, they're kind of oriented it really about being an educational type of thing. There is a UK college that is now in the middle of revamping their entire mathematical curriculum at the undergraduate level to actually use this. And their idea is that they really want this to become the new standard of teaching mathematics at the undergraduate level, which, because it relieves a lot of burden on TAs and stuff like that to go through and check these proofs, and also just gives students better tools to write them up. So they're not just writing, literally pen and paper, these massive types of things. So it'd be interesting to see what happens with that. It could be a real game changer in terms of education. So anyway, that's it on Rocq. Again, if you watched this all the way through, thanks, and do like and subscribe, and I'll see you in the next video.